All right, class, we're gonna get started. Okay. So announcements for today. God, take some candy. This week we have a few things going on. We're going to wrap up chapter 6 today. I'm just gonna move this this window out of the way. So we're gonna be wrapping up chapter 6 today. Then on Wednesday, we're going to do our midterm review in class, homework 8, which covers a lot of the concepts that we discussed last week on Wednesday. We've been discussing since then, is also due on Wednesday. And then on Friday of this week is midterm 2. Just as a reminder. Yeah, something scary to start your morning on Halloween. So another thing just to bring to your attention, I know there's a lot of things on your attention right now, but CFD project teams will be coming up. We'll form the teams just after midterm 2. You'll see a Google Sheet poll or Google Sheets thing go out to ask you about what teams you'd like to make. That'll come out just after the midterm. We'll be making groups of 4 to 5. As needed for those of you, especially sometimes with like transfer students who don't know as many people in the class yet, are concerned about this, but as needed, I will help you form groups. Okay, so don't worry, don't stress about it, but start thinking about what you might like as your groups. Finally, happy Halloween. So we have our, so some of your classmates made a Reynolds number pumpkin, which is great. So a good reminder of something that we need to remember for the exam on Friday. I can't tell that it's a Bernoulli pumpkin, to be honest, but apparently this is a Bernoulli pumpkin as well. Partial credit. Okay, before we get started, I think we are going to skip the videos for today in favor of spending more time on the pipe sizing example that we started on Friday, and an example of a couple more examples today. Yeah. Yes, I will be posting old midterm 2 exams. That will be today or tomorrow. Yeah, but that will be pretty soon. Yep, thanks for the reminder. Other questions? Yeah. Oh, so the last 2, yeah, I guess I might have removed that from this homework. But for example, the last 2 on this homework are directly from previous exams. Any true false questions that you've seen are also from previous exams. Especially as we get to the later midterms, those homeworks sometimes they come from a whole range of different previous exams, some midterms, some finals and everything. I'm just kind of putting together what we've covered. And so I've stopped trying to tell you exactly which exam they came from, but you'll see when you get to practice, you've seen a lot of the questions already. Okay. Yep. Yeah.
Just to confirm, everything we've gone through up through today is fair game.
Yeah, there's gonna be a break today where I'll say this is material in chapter 6 that is not on the exam. No, some elements of today will be on the exam. There will be a point in today's lecture where I say these last couple of slides are not covered on the exam. Okay, we are not there yet. So I didn't put it up here because the material that we're covering right now is essentially problem solving based on concepts we introduced last week, and that will be on the exam. Okay, yeah, there will be a point where we get to pumps and flow rate measurement that we haven't covered in sufficient time to put on the exam on Friday. Okay. Other questions? So just a note about the previous midterms. In particular, you're going to see the 2019 midterm will include a problem on external flow. I'm going to give it to you so you get a sense of timing, of like how long that exam was. But it's not something that we've covered in this class, so it's not something that I would ask you on the midterm on Friday, right? So we're going to cover external flow. So I've rearranged the class a little bit. We're going to cover external flow after the midterm. So when you see that problem, I don't know, you'll see it eventually on homework. But when you see that problem, don't panic that you don't know how to solve it. I understand you don't know how to solve it. But so it's not something that I would expect you to be responsible for in the midterm on Friday. Okay. Okay. Any other questions? All right. So last Friday we were talking about pipe sizing. And so this was in your text refers to this as a type 3 problem. And the question was, what is the diameter of a pipe that can support the given flow? And there were a couple of things that we got to right at the very end of class. I just wanted to make sure we hit again that make a pipe sizing problem a little bit different from the other types of problems that we might encounter in a pipe flow problem. So the first is, so as a type 3 problem, we saw that this is a type of problem that may require iteration, right? Because the friction factor depends on the diameter, and the diameter depends upon the friction factor. But another wrinkle in this type of problem is the fact that pipes don't just come in any size that you want, right? So we're given here a table of Schedule 40 pipe sizes. And the nominal size of a pipe is not equal to the actual size of a pipe. So in this case, our answer was that we wanted something of about half a foot or 6 inches as our pipe diameter. And the closest that we're going to get was this nominal 6-inch diameter pipe, which actually has an internal diameter of 6.065 inches. Okay. So that was one wrinkle here. And then the last one has to do with the allowable stress and the schedule of the pipe. And we're going to talk a little bit more about that after we just review what the answer was. So remember, when we're solving a problem that involves iteration, you're going to have to do the same calculation a bunch of times. And so the approach that your textbook takes, and that I would suggest as well, is to write out an expression, in this case, an expression for an expression relating the two parameters that you're going to be iterating over, based on what you know in the problem. So in this case, you're going to be iterating over friction factor F and diameter D. And so we're going to use this friction factor relationship to set up our iterations. And here, your text is using an alternate form of our friction factor definition. That's in terms of Q instead of velocity, because in the problem, we were given the flow rate Q. And so this makes it a little bit easier for us to plug everything into the expression. Okay. So we know neither D, the diameter, nor F. In this case, we knew that we had smooth pipes, so we were using the Prandtl formula. We could also use the smooth pipeline on the Moody chart, right? So just go back. So on the Moody chart, this is from our previous example, right? This is the Prandtl relation, or the relationship for a smooth pipe. So you could use this line on the Moody chart in order to solve the problem that we're working on right now. And then now that we have this set of equations, we can solve these iteratively. And remember, we looked at this on Friday. The way this example comes from your text and the way it's set up, it's a little bit confusing. It's read from right to left for some reason, where they started out with a guess for a friction factor of 0.02, which is just somewhere in the middle of the range of friction factor, right? We didn't have an epsilon over D. So ordinarily, when we have roughness of the pipe, we start out by guessing our friction factor as the value for a fully rough flow, right? We said that's generally going to be a pretty good guess when we have roughness. In this case, we have a smooth pipe, so there's no fully rough limit, right? We know that we're told that the pipe is very smooth, but we still need a place to start, and so we just started at 0.02, which is roughly in the middle of the range of friction factors that we typically get. So with that friction factor, we can then update the diameter. We can estimate the diameter of the pipe. From that, we can estimate the Reynolds number. From that, we update our estimate of F again using this expression or the Moody chart. When we go back, that comes over here, update diameter, update Reynolds number, update friction factor again, and so on until convergence. Okay. I do not believe that's possible with this expression. So I do not believe there's another local minimum, or there would be another spot that you would locally converge to. Yeah, that's a good question, but I do not believe that's true. Other questions? Yeah. Mm-hmm. Yeah, conceptually, why is it the diameter has such a huge impact on, let's start with pressure drop. So previously we saw that pressure drop goes as diameter to about the -4.5, I believe was on the slide. So meaning that a relatively small increase in diameter has a really large effect on pressure drop, right? Really creates a large decrease in pressure drop. So what we're seeing here is the impact of A squared, right? So remember, if we're relating velocity to flow rate, the velocity is, sorry, Q is equal to V times A, right? And so that's going to give us, that area is going to give us a D squared, and then this whole thing is squared again. So that's how we end up with a D to the 4th times this already D, and that's how we end up with D to the 5th, right? Intuition is it's a similar thing that's going on in the pressure drop relationship, where the diameter of the pipe, as we increase the diameter of the pipe, that increases area as the diameter squared, which gives us already a large power. That doesn't get us to 4.5. So I have to do a little bit more research, I think, to come up with the final answer to that. Yeah. Yeah. Let me get back to you on that. Can I do that? And look into it and get back to you, because I don't have an immediate answer for you. Yeah. That's a good question though. Yeah. Okay. Other questions? Okay. Okay. So in this case, we converge on 0.493 feet, which is close to 6 inches, but not exactly 6 inches, right? But rather than tell our pipe supplier that we want a pipe of 0.493 feet exactly, which would be very, very expensive, we're going to go with a nominal 6-inch diameter pipe, basically just the next size up. So 6.065 inches is going to work here. So now we have to look at the second part of the question was whether Schedule 40 is suitable if the pipe material has an allowable stress of 8,000 PSI. And the important expression here is that schedule number. When we say it's Schedule 40 pipe, what that means is it is 1,000 times the pressure, pressure within the pipe, allowable pressure within the pipe divided by the schedule. So in application here, so the schedule number is 1,000 times max pressure over allowable stress. So 1,000 times, so we have to find the maximum pressure in the pipe. In this case, would be at the start of the pipe, because the pressure is decreasing as we move down the length. When we have a horizontal pipe, pressure is decreasing as we move down the length. So the maximum pressure is at the inlet, 265 psi. And so when we compute what our minimum schedule number is, we get Schedule 33. So we need a pipe of at least Schedule 33 to support that maximum pressure. Again, schedule numbers don't come in any old increment you want. Schedule numbers are kind of round numbers. We have 5, 10, 20, 30, 40, 60, 80, and so on. And so we're going to choose the next biggest one that we can find. So in this case, we would choose a schedule 40. We'd specify a schedule 40 pipe, right? So schedule 30 would not work, right? The pressure within this pipe is too high. The schedule number that we compute is larger than 30, meaning that a schedule 30 pipe would not be sufficient. Basically, the wall thickness of schedule 30 pipe would be too thin to hold this pressure. So we're going to go with a schedule 40 pipe in order to hold this pressure. Okay. Okay. So, pipe sizing problem. So schedule 4, and of these, schedule 40 and 80 are the ones that are most common, right? So schedule 40 is sort of standard pipe. Schedule 80 is stronger standard pipe. So those are by far, if you're looking for, even if you go to Home Depot or something, you're going to see schedule 40 and 80. But those are going to be by far the most common pipe strengths. Okay. So we saw some of the nuances of this kind of a pipe diameter problem, right? So it is requires an iterative solution, right? Just like a type 2 problem. Remember, type 2 is where we're solving for velocity or flow rate. Also requires iteration. But when we're doing a pipe sizing problem, we require iteration. But then there's also some nuance in that pipes aren't available at any size that we want. So we have to follow what's available. We often are going to have to figure out the strength or evaluate the strength of the pipe and see if it's going to be sufficient for our application. Okay. Okay. All right, so the last type of problem, your textbook calls it type 4, is where you have to solve for the length. So this is not nearly as common as type 1, 2, and 3. Some textbooks leave this type of problem out because it's not often that you have to, most of the time the length of the pipe is going to be a given, right? You have to get your fluid from point A to point B, and they are a certain distance apart from each other. In this case, but we'll look at how to solve one anyway. So in this case, we're given that a pump delivers 0.6 horsepower to water 68 degrees. Given that it's a 6-inch diameter asphalted cast iron horizontal pipe at 6 feet per second, and we want to find the proper pipe length to match these conditions. The power, so this, we went back to our energy balance and our energy balance derivation. We can come up with this expression that the power of a pump we would express as rho G times Q times H pump. So the power in terms of the head developed by the pump depends on the density of the fluid times gravitational acceleration times our flow rate Q. And so from this, we can see that we actually, since we know the fluid, and we know the diameter, we know the velocity, therefore we know the flow rate. We can use this expression to straight away find the head that's being developed by this pump, right? So we know H in this problem, right? Or we have enough information to find H, right, from the outset of this problem. And so what's left is really just solving for that length, L. And we know that for a pipe, we have our head loss due to friction is F times L over D V squared over 2G. And we're asked to find this L. So we're going to find HF from the known power. So we know the velocity, we know the fluid, we know the diameter, so we can compute Reynolds number based on diameter. We know the type of pipe, right? Asphalted cast iron. So we can look up the roughness and find epsilon over D, meaning we can find F, right? No iteration required. We can just go to the Moody chart and find F. And then from that, we're going to solve for our length L. Okay. In this case, start by, so if you are approaching this kind of problem, say on the exam, start by writing out what you know, right? So it might not be immediately obvious to you that you know enough to plug into this power equation, right, to find HF. we are generally going to have to find Reynolds number, right? To solve one of these types of problems, you have to find Reynolds number at some point. So write out the formula for Reynolds number, and start computing your Reynolds number, right? Because you know that's going to be a step in solving the problem, right? Write out what you do know, right? So you see pump power, right? And you know that pump power is related to the head loss, or the head developed by the pump, in terms of this expression. So write this out, okay? See what it would take for you to, do you have enough information? Then ask yourself, do you have enough information to find the head developed by the pump, right? And you would see that you need Q. So then, okay, do I have enough to solve for Q, right? And then write out, and solve for Q. Okay. So as we're going through these problems in class, I'm kind of walking you through the solutions, right? And it's easy to sit there maybe and say, oh yeah, I know how to solve this problem, hopefully, from seeing it. But when you have a problem like this on your homework, right? So make sure that you are taking the time to sit down, look at that problem, decide on the approach yourself. Remember that, for example, on the exam, the thing that I want to see most of all from you is that you know how to set up and start to solve the problem. Okay, so make sure you're practicing that on the homework. Okay. So we need Q in order to find the head developed by the pump. And so, but we know the diameter, so we can find the area, and we're given the velocity. So we find Q. Then we can plug into this expression in order to find the head developed by the pump. And now we're going to say that the head developed by the pump, basically the energy that the pump is putting into the system, is going to be lost due to friction along the length of the pipe. And so we'll set that head developed by the pump equal to F L over D times V squared over 2G. And again, we know V, we know G, we know D. We have to find F, but we have enough information again to find it. We have Reynolds number, we have epsilon over D. Right, so we find our Reynolds number, we find our epsilon over D. In this case, your text shows using the Haaland approximation instead of the Moody chart, but you can use the Moody chart. You could use the form of friction factor. Actually, no, sorry, this is the Colbert equation, sorry. And you can use the Colbert equation, which requires some iteration on its own to solve for F. Then we get F is 0.0198. And then we can find the pipe length from this expression, right? Plug in and find the pipe length. Okay. All right. Any questions on this? Okay. So another type of problem, again, that we introduced last week, but another complication that you should know how to deal with are minor losses, right? So remember that, so we said real pipes have roughness. They don't come in any size you want. Real pipes also have fittings, right? So we can actually, connect them to other devices and other pipes and so on. And so we need to know how to account for minor losses within our system. So this type of problem is going to involve dealing with those minor losses. Another complication in this problem that I want to make sure that you're aware of, that you'll see in the homework, or that you've seen in the homework if you've started looking at this already, is that we're going to be coupling a pipe problem to basically an energy balance. All right, because remember the pipe flow expression that we developed starting at the very beginning of this chapter just comes from the energy balance approach from chapter 3. And here we have flow coming into our pipe system from a reservoir at a specified height. And then we have flow coming out of our pipe system into another reservoir at a different height, right? And so in order to solve this problem, we're going to have to do an energy balance between point 1 at the free surface of that reservoir 1 and 0.2 at the free surface of that reservoir 2, where part of our energy balance is going to be accounting for the loss due to friction as we flow through the pipe. Or part of our energy balance is going to be the difference in gravitational potential energy between those 2 points. And another piece of our energy balance is going to be the energy that we're putting into the system with this pump. Okay. So in this case, we're asked to find the pump horsepower required. So when you see that pump horsepower required, what type of problem is this? 1, 2, 3, 4. Any guesses or statements on what type of problem that is? We have to find pump horsepower. 4 is pipe length, right? But very similar to 4. I see number 1. Why is it number 1? Yeah, we're looking for power. That depends on the pressure loss, which we've been expressing as the head developed by the pump, right? Or the head loss across the whole system. And so this is basically a head solve for head type problem in disguise, right? So a type 1 problem. Okay. Because again, we just go back here, the power, right, that we require from the pump is rho g q times h pump. So really we're being asked to solve for h pump and then plug into this expression. Okay. Okay. So and we're given roughness ratio, we're given the kinematic viscosity, and in this case we're given the flow rate, right? So really the only thing that we're missing is that h pump. Okay, so our approach is going to be energy balance. So the steady flow energy equation between that 0.1 and 0.2. So we have P1 over rho g plus V1 squared over 2g plus Z1, right? So the energy of the fluid expressed in head at 0.1, right, all the way up there, is equal to the energy of the fluid at 0.2, right, which is going to be the free surface of that container on the right-hand side. I'm not even going to attempt to get there. Plus the head loss due to friction, right? So the frictional losses through the pipe system, plus all of the minor losses, right? So we have fittings here, bends and valves and so on, minus the energy that we put in to the pump, from the pump. Okay. So in that expression, is there anything that I can drop out right away? Why can I drop out velocity? I hear 2 answers, and one of them, yeah, one of them is actually the right one. So what did you say? It's static. What do you mean? Why is it static? Yeah. So did anyone not get that? I heard some other answers like that it was equal. So in this case, the V1 refers to the velocity at the upper surface of this tank, okay, where we're in a static condition, right? We're going to assume that this is in a static condition. So V1 is not the velocity in the pipe, okay? V1 is the velocity at the surface of the tank, and we're going to assume that's 0, right? V2 is the velocity at the surface of this tank, and we're assuming that that's 0. So yeah, question. Technically, the water levels are moving. I mean, in this case, in this type of problem, so you'll see in the exam, I would give you, for example, the area of this, and you would see that the area of this is much, much larger than the area of the pipe. Or I would tell you that the area of this is really, really large, which tells you that the water level here is not going to change very much. Okay. Yeah. You know, and you'll see on those exam problems, for some of them, I am asking you to eventually find how the water level, how the liquid level in the big reservoir is changing, right? But on one of those problems, I tell you, you can make a quasi-steady assumption where you assume that basically this level is not changing, right? So this velocity is approximately 0. Okay. Okay, so V1 and V2 are 0 because those are the velocities at the free surface. And P1 is equal to P2 is equal to P atmospheric. Okay, because these are at the free surface. So those are going to drop out as well. Your text then simplifies this, right? But applies those expressions and simplifies this. So the only thing we're left with then from the energy of the fluid at section 1 and energy at section 2 is just Z2 minus Z1, right? So we have the power that we require, or sorry, the head that we require from the pump is Z2 minus Z1 plus the head loss due to friction through the pipe plus all of the minor losses. So just for a second there, just want you to think about that, just conceptually. What this is telling us is that the energy that we're going to put into the fluid, right? The energy that we require to move the fluid from this tank to this tank has to overcome 3 things, right? The elevation difference. So there's a gravitational potential energy difference between condition 2 and condition 1. We're pumping water uphill. That takes energy, right? So that's one component. We also have to overcome the friction within all of these runs of pipe, right? That's that HF. And we also have to overcome all of the minor losses, right? So all of the frictional losses because of this half open gate valve, right? Because someone didn't open the valve all the way. Because of this open globe valve, that's good. Because of this bend and elbow and everything, okay? So that's what this expression is telling us, okay? So it's statement of energy balance and the energy that the pump has to provide. Another thing I want you to note is that we're not going to have a minor loss coefficient for the pump. Why are we not going to have a minor loss coefficient for the pump? It's going to be built into that head loss from that head developed by the pump. Exactly. So we said that any losses or anything that any frictional losses within the pump itself, and we're going to include, you know, the connections and fittings and whatever that connect the pump to the rest of the pipe. Any of those energy losses, we're just going to lump into this HP term. Okay. Okay. So now with the flow rate known, we can calculate our velocity. So we know our flow rate, we know the diameter, so we can calculate velocity. We have a number of different minor losses. So we're going to go through to the tables in our text or the information that's provided or the manufacturer data sheets. If we were doing this, you know, on a real system and find all of our minor losses, right? So we look them up, right? In all the tables and charts and things. Yep.
So out of curiosity, if we had a really long length of pipe, would we typically neglect the minor losses just to make the calculation easier?
Yeah, so if we had a really, really long length of pipe and these things, and we don't have very many fittings, then yeah, you would probably neglect these because they would be truly minor. But we'll look at this in just a second. We'll see how this compares to the losses, the frictional loss through the pipe itself. In this problem, these are significant. They're not major. They're not the major frictional element here, but they are significant. But yeah, if you had a really, really long run of pipe, you would likely ignore this guy.
And one more thing, with the length is with the total fence of the length, like the total length of your draw line.
Yeah, so in this type of thing where we have the, we're going to assume that the length is the total length of pipe that we have, not including the fittings, basically. Yeah.
So like that bend.
Yeah, so you wouldn't have to like go in and do the geometry of like, oh, how much pipe is in, how much length is in this bend? You would just either assume that's negligible or just ignore
just the
that.
length of the straight.
Yeah, so think of the length as the length of the straight pipe. That's right. Yep. Yeah. Yeah, so in that case, you would have, yeah, so good question. So if we had 2 sets of pipe, right, of different diameter, then we would have a head loss due to friction in the first pipe, and then a head loss due to friction in the second pipe. And then we would end up with a minor loss for the exit from the first pipe into the second, and then another minor loss for the next one. That's correct. Yep. Yes, and we would have to keep track of our minor losses separately for pipe 1 and pipe 2 as well. Okay. Yeah, so you treat them as 2 different pipes. Okay, so we sum up all of our minor losses. Calculate our Reynolds number, 139,000. So are we laminar, transitional, turbulent? Turbulent, definitely turbulent. Okay. So epsilon over D, 0.001. So we're going to get a friction factor 0.0216. And therefore, then we can plug in here and find that our head developed by the pump is 100 feet, right, to overcome the gravitational potential energy, plus 85 feet, that's to overcome the frictional losses. So we get 185 feet of pump head required. I just want to talk for a second about this. So this term here, this is FL over D, right? So we rewrote our HF plus sum of HM as our V squared over 2G times the quantity FL over D plus sum of K. So this is FL over D plus sum of K is what's in this bracket here. And that FL over D works out to 51.8. Our sum of K was 13.4. So we can see these minor losses, they added up to be significant, right? Certainly there would be significant error if you left out the minor losses. But in this case, they were not greater than the loss through the length of pipe. So the question was, you know, in some cases, might you ignore the minor losses? So if your length, for example, was really long, then this thing would get much, much bigger, could get much bigger, right? The FL over D term could get much bigger. And if this were much larger than 13, then ignoring this would not, in this problem, would not be that big of a deal, right? And so for a really long run of pipe, yeah, you might ignore the minor losses. Although in this case, you could not. Okay. Okay, but we still need to find the pump horsepower, right? So we need to find the power. And so we're going to say the power, rho GQ times HP. And working that out, we end up with about 4.2 horsepower, okay, as the power required by the pump. Yes.
I've done a little bit of work with this in the past with the job, and providing K, I think they're dependent on other things, like what are the difference between all three numbers? The size of the fitting, or the size of the pipe.
Yeah, so K is going to depend on many things, and it's something that we have to look up. And then it would be, eventually you're going to get to a number for a given problem. But for example, here we had half closed gate valve, right? So that means you'd have to look up the data for gate valve. In this case, it's a figure in your text, or a figure that I might give you on the exam or something, right? Or a figure that you look up from the manufacturer. And you would find the loss coefficient for the valve when it's in the half closed position, right? And that loss coefficient for the valve in the half closed position might depend upon the size of the fitting, and it's going to depend on the manufacturer of the fitting. So all of that would be included in what you look up. Yeah, I mean, the only one that's a straight number is for a sharp exit. We know it's 1. But for everything else, there's going to be some kind of calculation or lookup or find the right table or find the right figure, that kind of thing. Yeah. Yeah, good point. So another thing that we would have to account for in a real problem would be pump efficiency, typically about 70 to 80%. Included in this pump efficiency are all of the minor losses and things, right? All of the frictional losses because of the inlet and outlet of the pump. That's where that would come into play. So a 4 horsepower pump. So if the manufacturer says the horsepower, the pump power is 4 horsepower, it's likely not actually going to be enough for this problem. We'd have to account for the pump efficiency as well. Yeah, so 6 or more, right? Horsepower. Yeah, go for 10, yeah, and know you're safe, right? Yeah, but we would have to account for pump horsepower as well. Or sorry, pump efficiency as well. All right, any questions on this? Okay. Okay, so multi-pipe systems. So we talked about this as well last week, but and you have an example on the homework. In this case, we want to see, we're trying to find the flow rate given a pipe system that's shown there, the total head loss, and the fluid, right? We have a table of specifications for all those different pipes. Okay. So these pipes are in parallel. So that means that the head drop across each one of those pipes is going to be the same. Think of head here is as representing pressure. So the pressure drop across each one of those pipes is the same. Okay. Because they're all connected to the same points, those points A and B. So the difference in pressure across all of those pipes has to be the same. And then the total flow rate is going to be the sum of the flow rates through all three pipes. In this case, this is a type 2 problem, a flow rate problem. So we're going to have to solve, we're going to end up having to iterate. So we're going to start with our HF expression. And in this case, we're going to solve for, we're going to write this out for each velocity separately, for each one of the pipes separately, V1, V2, V3. Actually, in this case, go through the iterations on all three pipes. So we're going to guess we're going to start with the fully rough estimate in pipe 1, get our friction factor 0.0262. From that, we'll get our velocity, Reynolds number, update our F1, and 2, again, we're going to start out with a guess based on fully rough of 0.0234. We'll do the same thing for pipe 2, and then for pipe 3, we're going to do the same thing as well. And in this case, we'll see that for each one of these problems, right? So we basically just solved 3 type 2 problems in parallel, right? 3 type 2 problems in a row. And then, and from that, we'll end up with we'll be able to find our final flow rate, which is just the sum of all 3. Yes.
If they were all the same diameter.
Yeah, then you just have to solve it once. If they're all the same diameter, they're all going to have the same flow.
But the friction factor, the head loss is the same.
Oh, sorry. Yeah. No, you're right. Yeah, if they're all the same diameter, yeah, then you would be able to guess. Yes. Sorry. If they're all the same diameter and length, then the flow rate in all of them is going to be the same. But yeah, they are different lengths in this problem. Sorry about that. Yeah, so you could use what you know from the first problem to help you in the second one. Yeah. Okay. So you'll have some practice on this. You'll see this on the homework as well. There you'll see the simplification where it's for a heat exchanger with pipes that we're going to assume are all the same diameter and all the same length. A bundle of pipes that's all the same diameter and all the same length. So instead of having to solve one, a different pipe flow problem for each pipe that you have in parallel, you just have to solve one problem and then take the flow rate that you get from one pipe and multiply it by the number of pipes, right? But in general, when we have pipes in parallel, for example, it's not. It's basically the same type of problem that we've already encountered. Okay. All right. Any questions on this? Yeah. I will try to give you all the minor loss. I will try to give you tables and charts of important minor loss coefficients. Yeah, I will try to give you all that you need. I'd still suggest you know where that is in your textbook. Pipe roughness chart I will put on there. Yeah, not important information. Yep. Okay. So here's a more realistic pipe network than what we've dealt with. So real pipe networks are obviously way more complex than what we've been dealing with in this class so far, and what we can do by hand. So computational tools can be extraordinarily helpful, right, for solving real world problems. So Professor Whitty is going to give us a guest lecture on November 14th on how to use Aspen for solving some pipe flow problems. Just as a brief introduction to the type of tool that you might use in order to design a more complex system, right? And when generally we're not just running in a plant or something, we're not just running a run of pipe just to lose friction, right? We have runs of pipe to get from one piece of equipment to another, and so the solution to our pipe flow problem might depend upon the solution to what's happening within our boiler or something else, right, or some other piece of equipment. And so their computational tools are definitely required. But we'll get an introduction to that. and a brief homework on that afterwards on November 14th. Okay. All right. So there are two more topics in chapter 6 that we didn't introduce last week, and I don't want to introduce this close to the exam and then put on the exam, which are pumps and flow rate measurement. We're going to hit the high points of pumps, and we're going to save the flow rate measurement for after midterm 2 in our last couple of minutes today. And again, this is not on the midterm, but it's included in the material in the class, could be on the final. And definitely is the type of thing that you might encounter, post-graduation with a chemical engineering degree. So we've kind of simplified, and we said that pumps in our pump problem earlier, all we had to do was find the head provided by the pump, and from that we got power, and maybe we apply an efficiency in order to figure out the pump power. But in reality, for a pump, the pressure rise or the head increase provided by the pump is a function of the flow rate. And so there's an additional dependency in a real world pump problem that's not captured in what we've looked at so far. Yeah, exception would be positive displacement pumps, but those are not that widely used. So your textbook goes through, gives some examples of multiple different types of pumps that are out there. And each of them will have their own pump curve relating the pressure rise or the head increase to the discharge or the flow rate through that pump. This is what you would typically see. And so you can see for a positive displacement pump, we have nearly a vertical line. But this is more typical of what we would typically see. Because oftentimes, one of the pumps you're very likely to encounter is a centrifugal pump. They tend to be, right, for a given capacity, they tend to be fairly small, simple, and robust. So they're very widely used. And this is typical of the pump curve for a centrifugal pump. And so what we see, so these blue lines here, let's start with these blue lines here. What we would see is that the head that the pump is capable of developing declines moderately with flow rate until it gets to some critical value where it starts to really sharply fall off. Okay. And we'll see, so going into the details of specifying pumps based on one of these charts is actually going to be beyond the scope of what we're going to cover in this course. I just want you to be familiar with the idea that it's not all just about specifying the head that's provided by the pump, right? In actuality, specifying a pump goes a little bit beyond just that. And so there are some other design criteria, right? And because you have to account for the fact that as you increase the flow rate that you are requiring by the pump, you are going to be decreasing the amount of pressure that the pump can provide. There are some other design criteria, including the net positive suction head, NPSH. So that would be the head required or the pressure required at the pump inlet to prevent cavitation. Basically, in one of these pumps, you have this impeller that's spinning around and around and ejecting fluid as it spins. And that ejection of fluid is what's actually pumping the fluid through the system. But now, as you're doing that, you have regions of high velocity, and those regions of high velocity create low pressure. Right? Think back to Bernoulli equation. And if that pressure gets too low, then you create cavitation bubbles, which can cause pitting and damage to your impeller. Right? So it's a major source of damage to impellers in this kind of a pump. And so the way to avoid that is to make sure that your inlet pressure is high enough that the pressure inside the system never gets low enough to create cavitation. And so that's that NPSH. Pumps will have a specified power. That's a parameter that we looked at previously. And that typically would be the power, the overall power after factoring in the overall efficiency, right? Which again is going to typically be about 70 to 80% for this type of pump. This total efficiency considers all the different kinds of losses, including the fittings, for example, on the inlet and outlet of the pump. Okay, so we're going to end it there. We're going to come back to measuring flow rate after midterm 2, but on Wednesday, we're going to do a review for midterm 2. Happy Halloween and thank you all.